This will be death by PowerPoint. When we take our first radio tests, they do ask you something about repeaters, and this is usually the image that sticks in your mind. I can't talk to the guy on the other side of the mountain, but that thing up there can, and that's what lets me talk long distances on my little radio. Hopefully we will end you up with a lot more knowledge about repeaters. Imagine you're standing in a big area, like maybe an airport terminal, and somebody's standing next to you who's quietly giving you some dialogue, and you have to simultaneously yell that dialogue so that people all across the terminal can hear you. What kind of problem do you think you'd run into? Probably you wouldn't be able to hear the person talking to you because your own voice was so loud you drowned them out. Well, that's pretty much the problem that repeaters have. They're trying to receive very weak signals, sometimes really weak signals, on the same band and at the same time as they're transmitting a very strong signal. And more often than not, they're co-located with a bunch of other repeaters, which means you have at the same location a lot of other transmitters putting out strong signals. When you're sitting there on your handheld in the living room with a rubber duck and you wonder why people can't hear you, maybe that will give you a little better idea of why they can't hear you. What we're going to try to do here is give you an idea of how you can better do your job as a radio operator. And what is that? It's to be heard clearly, among other things. In order to be able to be heard clearly, what can you do to basically put a better signal into the repeater? We're going to focus on 4 factors. The first one is location. We've on some of the simplex nets we've had on Sunday mornings that Dan and our 6V hosts, we've had people that are very difficult to hear, and we ask, where are you? Oh, I'm inside on my sofa. That first line on the first slide was not a joke. Some people do that. And we said, well, try going outside. And magically, their signal gets a little better. I've heard people say, well, I have a nice mag mount antenna, and I put it next to my radio on a cookie sheet. That may be a little bit better than the rubber duck on the handheld. It does give me some concern about how much RF is going into their cranium, and I suggest that they not do that. Generally, outdoors is better than indoors because you don't have the obstructions of the building. Higher is better than lower, with one caveat, that is, don't use so much crummy coax to get your antenna higher that you lose all the signal before it gets to the antenna. And the fewer obstacles, the better. If you can get to a spot on your property where you're not blocked by a building next door or something, that would be really helpful. It would also be good to know where the repeater is relative to your location. You can get maps to do this, and use a compass. Say, hey, what direction is Verdugo Peak from my house? And get out and look at that. Okay, what's in the way? And you may realize that maybe by going to the back of the property instead of the front of the property or something like that, that you have a better shot. So in all these things, you should be able to try out. There'll be people on the machine who will help you listen and decide which gives you the best result. So let's move on to factor number 2, antenna systems. Okay, now notice I didn't just say antenna systems, which includes the feed point, the feed line, and so on. I'm sure you all know that a rubber duck little antenna that comes with your handheld is not very efficient. It's got, it's typically a coil wound around some sort of inert substance, and then it's got a coating on it. Coils are less efficient than straight lines. And you know that a quarter wavelength on 2 meters is about 19 or 20 inches, and you know that rubber duck isn't anything close to 19 or 20 inches. So it's not going to be very efficient. If you're in a strong signal environment, like where you're all in an auditorium, or you're walking around a football field or an incident or whatever, and you're going simplex from one to the other, that's probably fine, and they're certainly convenient. Full length is going to do a lot better job in terms of laying down a signal. The good part about antennas is that they don't have to be connected to your hand or your radio. They can go where you can't. They can stand on the roof when it wouldn't be safe or prudent for you to do that. When you have a location for the antenna, if you have some gain on that antenna, that can help you out too. Now okay, what is gain? Gain basically means favoring some directions at the expense of other directions. And gain can work in your favor if you use it correctly, or it can work against you if you use it incorrectly. Basically, if you're using it correctly, less of your antenna's capture power to receive a signal and less of your transmitted signal will be wasted by going in undesired directions. And you see example is straight up. Well, what's straight up? Let's take a look. Here's a pattern for a typical omnidirectional vertical. So the vertical antenna, and we'll show some examples. This is a typical vertical antenna pattern. That is, most of the signal is going out within, plus or minus 30 degrees of the horizon from an elevation standpoint. And when you get up close to straight up, there's almost no signal going straight up or no signal going straight down. That's the basic pattern. If you get you know that if you go from a GP3 to a GP6 to a GP9, the antennas get taller. There are more segments inside that little white radome. And what that does is take that donut shape that you see and flatten it out. Instead of 30% of your signal going up at 40 degrees, now it's only maybe 10%. And instead of the horizon seeing about 50% of the signal, it sees about 75%. It squishes that down. Eventually, if you have enough gain on an omnidirectional vertical, you would have basically a flat pancake pattern. The horizon sees everything and pretty much nothing else. That's one form of gain. Here are samples of omnidirectional verticals. A little NMO here in the middle, typical mag mount. This looks like probably a 400 or 500 megahertz business band, and then a ground plane vertical. Remember, by the way, that quarter wave vertical is basically a monopole unless there's some other half of the antenna. The other half, in the case of a dipole, it's easy. You got two wires, and one connects to the shield, one connects to the inner, and they carry the current pretty much equally. In the case of a vertical, you don't have a second wire as such, but if you have a ground plane vertical, such as this one here on the left, you have several wires that act as the other half of the antenna, if you will, to help steer the pattern. In the case of this NMO mount in the middle, what's the other half of the antenna? It's the metal surface that it's mounted on. And so that could be the car roof, for example. Or I suppose, any sheet metal that you have that thing mounted to would be kind of the other half of the antenna. In the case of the mag mount, it's a little tougher because the magnets help adhere the antenna to its mounting surface, but there isn't necessarily a good RF connection between the shield of the cable that is carrying the RF from your transmitter and the surface that it's mounted on. Mag mounts tend to be less efficient. They do work, but a little bit less efficient than something that's mounted where there's a good electrical connection to the underlying surface. Okay, so that's omnidirectional verticals. You can have directional vertical antennas too. Now let's take a look at these patterns. On the left, you're looking basically sideways at the antenna. You see basically almost nothing's going up or down, but you see between about 30 degrees elevation and minus 30 degrees elevation. You've got maybe at least 2/3 or half your power. The biggest bulk of it is going straight out at the horizon, and that's a good thing. Normally that's what you want. The next on the right, you're looking top down on this same antenna. So not only do we have gain favoring the horizon over up and down and so on, but you also have gain in the azimuth plane, that is looking down the compass directions. More signal is going, in this case, north if it's 0 degrees. Less of it is going east and west. Very little of it. In fact, there are nulls off to the sides, and there's a much lower level going out to the back. Remember, if you were looking down on an omnidirectional, like a vertical, on this right-hand picture, it would basically be a big circle because it would be putting the same RF out, admittedly at a low angle here, but it would still be putting the same RF out in all directions. And let's say you live down at the port, okay? Well, how much really do you need to send signal to the southwest, out to the water, out to the ocean? You really don't. So that's the kind of situation where maybe something with some azimuth gain, some gain in the horizontal plane would be helpful. And by the way, gain applies equally to transmitted signals and received signals. The fact that you're sending and you're able to be heard better, maybe by a repeater or somebody else, is one benefit. The other benefit is that you can hear that signal better because more of your antenna's capture is facing that direction and less of it being picked up off the back and the sides. What would these things look like? Here are a couple of examples. I'm sure you've seen yagis. There was two Japanese guys, Dr. Yagi and Dr. Uda. Dr. Uda actually came up with the design, but Dr. Yagi got his name in first place, and that's what they're called generally. But they're officially called a Yagi-Uda array. And the coax connects to this driven element, this second one that looks like it's a little thicker than the rest of them. And that is called the driven element because it's driven directly by the coax. The other elements are parasitic elements. In the back is called a reflector. You notice it's a little longer. In the front, there'll be one or more directors, and you notice each director is a little bit shorter than the other one. And they're spaced such that they take what would be, if you didn't have any parasitic elements and you just set this here, this would be basically a vertical dipole. It would radiate pretty much in all compass directions, except for a little bit of interference from the mast, maybe if it's a metal mast. But because of the reflector and the directors, it gives you this kind of pattern that we were talking about here. Okay, now here's another directional antenna, and this is called a quad. Gee, I wonder why. Quads have been built for a long, long time. It's basically, each of this is a full wave loop, and you say, well, yeah, but there's one loop nested inside another. Aha, this is actually a 3-band quad, probably for 2 meters, 220, and 440. And I would estimate the cost to build this antenna is probably less than $10. It's house wire, number 14 TW, a couple of connectors, some scrap lumber, and a little bit of a few nuts and bolts. In this case, you've got a driven element, is this one right here. You can see there's the 2 meter driven element. Inside it is the 220, inside it is the 440, probably fed by different feed lines. And then in the back, you have a 2 meter reflector. You may have a 220 here. You don't necessarily have 4 elements on all 4 bands, because the spacing between the elements for 2 meters is one thing. The spacing on 220, see 220, the reflector has to be closer, and the directors here, and 440, it looks like it's just 2 elements here. So, but you could build something like this very cheaply if you just want to cover, say, 2 meters. The dimensions are basically a quarter wavelength. So think about the length of quarter wave whip on 2 meters, about 19 or 20 inches, 20, 40, 60, 80. Okay, so there's less than 7 feet of wire. And you could make a single loop element. You could add just a reflector and have just 2 elements. You could add a director and make it 3 elements. I could add another director and make it 4. You've got a lot of choices, and this is something that we can do ourselves cheaply and have really good results. Remember, we mentioned antenna systems, which means more than just the antenna. That also includes the transmission line, which is what carries the signal from the radio's output to the antenna, and the received signals from the antenna back to the front end of the radio. I do a separate talk, and some of you may have gone through this already, on choosing the right coax, and we talk a lot about coax characteristics and so on. But the simple rules for tonight, we're just going to say, first, you want to keep the losses to a minimum. If you envision coaxial cable as panes of glass, and the longer the cable, the more panes of glass are stacked one in front of the other. Now you can imagine if you stack enough of those together and they're anything but crystal clear, you're going to start losing light. Well, the same thing is true here. 1 or 2 panes of dirty glass can make it really hard to see anything. A couple of lengths of really bad high loss coax can lose most of your transmitted signal and most of your received signal. Say, well, where does my transmitted signal go? It goes as heat. If you use better quality cable, it's like a very clean, clear piece of glass. You can stack more of those together without losing all your light. Same with good coax. You can have a longer run with good quality coax without losing so much of your signal. All coax has loss, but you can keep those to a minimum. For the things I do competitively, I try to make sure that my target is to lose less than 1 decibel, which is to say I lose less than, say, 20% of the transmitted and received signal. My goal is to have at least 80% of the signal that hits the antenna get down to the radio. Sometimes I achieve it, sometimes I don't, but it depends on the band and so on. That's really easy to do down on HF, on the lower HF bands like 80 and 40 meters, where we have some of these Callaway S nets. But it's pretty difficult to do when you're up at 432, and very difficult when you're up in the microwave bands, because the higher the frequency, the higher the losses. The losses basically go up as the square root of the change in frequency. Good quality coax with the proper connectors can make a big difference. I'm working on another set of cables for a friend, and one of our ACS members has one, and he's really happy once he got it strung up there. Instead of copper braid, the shield of this one is corrugated solid copper tube. It's got very low loss compared to the stuff that we typically use on field day and so on. Proper connectors, clean connectors, put on right. So try to keep the cable not a lot longer than it's needed. For example, if I have a Andrew Heliax and I need to go 40 feet out to an antenna, I'm really not going to gain anything by using my 150 feet of really good coax, because I'd get the same result if I had coax that was 3 times as lossy, but only 50 feet long. After antennas and transmission lines, next factor is going to be transmitter power. I remember sitting on a net once, and we had somebody decided to act as net control. They offered, and that was volunteered, and it was nice of them. A bunch of us were having a really difficult time hearing him. And it turns out he was trying out his handheld on extra low power. He just wanted to see what it was like. Yeah.
Hey, Marty, there's a question from AJ. And does it make sense to use ladder line for longer runs of cable for UHF and VHF?
Good question. Ladder line, which basically it's parallel transmission lines, parallel wires, it's not coaxial. They do have much lower loss, and in fact, some stations have used those in big moon bounce arrays where it's like a fixed array pointed toward the horizon. The problems with that are every time it gets near something metal, like a rain gutter or something like that, it's going to interfere significantly with its ability to carry the signal. Also, it's much more physically fragile than coax is. The wires are more often than not solid wire. They can get work hardened by twisting in the wind. There's some things you need to do, like put it in maybe one twist every 10 spacers or something like that, to try and minimize the amount of it's going to be blowing back and forth in the wind. If you have a real long run, you could send the signal clearly. You might be able to do that. Now remember too that a typical ladder line or open wire line is going to have a significantly higher impedance, typically anywhere from 300, 600, 900 ohms, and so on. So you're going to have some sort of means to convert that impedance to the impedance at the antenna and the impedance at the radio. And those devices will have some losses in them, not as significant as super long length of coax. So yes, it's certainly feasible, but there are some physical limitations. You can buy pre-made, it's called ladder line or window line, where if you look at a length of it, about half of its total length is cut out in little square windows where there's almost no dielectric, just the wires and a little bit of coating between the next block of plastic. You could experiment with it a little bit, but again, matching the impedances is going to take a little doing, and probably some test equipment that most of us don't have. You never know till you try it. Let's go back to power. Trying to run the net on extra low power handheld, it was a fun experiment for him, but it made the net miserable for everybody else. Having more power will boost your signal strength into the repeater. Now, of course, it won't help your ability to hear the repeater. It only affects the transmit side. But if you're hearing the repeater quite well, and people just are having some trouble hearing you, adding some power would be helpful. I don't suggest you go out and buy, this handheld has 7 watts instead of 5 watts. No, that's really not the answer. First, the difference between 7 and 5 watts will be negligible. Second, you're getting to the point where you don't want that much RF sitting next to your brain while you're talking on the radio. That's why we encourage our members and really require of the lead guys and gals to use a mobile rig class, 25 to 50 watts. By the way, there's some mobile radio makers that outputs up to 70 watts. I don't really recommend that either. At some point, there's going to be so much RF in your car, you're going to have an RF exposure issue again. So, 25 to 50 watts is good. Try to use enough power to get a nice clear signal into the repeater as reported by those you ask. You don't necessarily have to use the maximum power available. Just because the maximum setting or high is 50 watts doesn't mean you need 50 watts. Try, mid 1 or whatever it is on your radio, maybe that puts out 25 or 30 watts. That may be quite adequate. And that also means that the electronics in your radio won't be heating up quite as much, and heat is the enemy of all electronics. If you use a little less power, it will keep things a little bit less heat stressed, and probably be enough. So try different settings and see what works for you. When you find one that's high enough to be heard well, you can stop there. You've also heard people trying to either check into the net or give a report, and they fade out, they just die away all of a sudden partway through. Usually that means they're using a handheld and they're using the battery that's in the handheld, and they either didn't charge it or the battery hasn't been properly conditioned or whatever. It's not made for long transmissions. You should have your radio powered by an AC power supply or a large, I mean, too large to fit in your handheld battery. Bioenno and other deep cycle batteries that we looked at are good choices. Back some time ago, I came across a supply of little 10, I think it was 10 amp Astron AC supplies, and we got a bunch of people those. That would do a beautiful job of running a handheld at full power, and even a mobile radio on low power. But a good AC supply means that as long as you have shore power, you can generate more than enough DC current to run your radio properly. You should take a look at the rating of a power supply. Just because it says it's a 12 amp supply and your radio says, the manual says it draws 10 amps. 12 amps may be the peak power, but it's rated for a continuous 6 or 7. Okay, so that may not be adequate after all. And of course, most of the work we're doing is on FM voice or digital. And in both cases, FM, whether you're modulating it with a computer signal or a voice, is 100% duty cycle. That means from the minute you go to the transmit mode, it is putting out full power as much as you have set it to put out, whether you're talking or not, whether there are any bits going out or not. That's a stress on a power supply if that supply is only marginally able to put out that current for short bursts. It's not enough to keep it going, all night or to run the net. Try to oversize the supply a little bit. Likewise, oversize the battery so that you have plenty of reserve, and that will also generally improve the quality of your signal. If you've got voltage that's diving, sometimes that will make your sound a bit weird, and the signal will not be really reliable. We've talked about location. We've talked about antennas and feed lines. We talked about transmitter power. This is all equipment. So now let's talk about the human factor, and that is techniques and operating skill. First thing, speak clearly and use phonetics. I don't know how many of you have ever gone to maybe your kids or your nieces or nephews' school play, and it starts out with some dialogue. A couple of characters are up on stage talking. And unless the kids have been well trained and well coached, they speak as though they were right next to the person, which they are, and they speak quickly and with very little projection. So the person next to them hears great. It's just like they're talking in the schoolyard. The audience can hardly tell what they're saying. It just kind of goes by in a blur. When somebody's speaking in a large room, doing a presentation in an auditorium, that's time to slow down. Try to make sure that you don't rush through what it is you're going to say. That's not the sign of a savvy operator. Sometimes it's the sign of somebody who doesn't understand that their job is to be understood by the person on the other end. I know I am sometimes guilty of speaking very fast, and I have done that. I have to remind myself when I'm talking to a group to slow down, leave a little space, and try to enunciate a little extra clearly. And that works well on the radio also. Use phonetics. Most of you are very good about that. We train for it, but you'll hear people check into the net without phonetics and they just rattle off a call. Some of these letters all sound the same. Net control has to come back and ask them to use phonetics so that they can get the proper call sign. Don't make net control come back and ask you. You give it the first time. Following net control's instructions. Those of you who have taken a shift or 2 or 3 as net control, either of our Monday night net or of our daily midday nets. You've had cases where you're calling for battalions 1 through 6 and somebody calls in from battalion 12. Now maybe they just tuned in and weren't sure they were going to get missed. Stop and listen. If you're not sure what net control is doing at the time, wait until you know what they're doing and jump in there when the appropriate time comes. A couple of people came in off schedule. I said, okay, we're not to your group, you're not to your battalion yet, but I've got you in the log. And when I get to their battalion, what do? They called again. What part of I've got you in the log isn't clear? Listen to what net control is saying and try to follow it. It will make the whole net go more quickly. You don't want to keep everybody else around wasting time or covering up some other poor person who's having trouble getting in, and you're calling again after you've already been heard. So if you're on Echolink, there is a significant delay, internet propagation delay on Echolink in both directions. And I have heard somebody calling in on Echolink when it's not time for Echolink, and net control is reacting as though that person were on the radio, which means when they stop talking, he or she acknowledges that check-in. But the acknowledgement was never heard because the internet hadn't finished sending all the signals back and forth. So then the person calls again later. I didn't get my acknowledgement. Well, yeah, that's because you called when we were on the fast turnaround mode of radio as opposed to the slow turnaround mode of Echolink. There's a reason we separate those, a good reason, because net control is working with a fairly predictable delay. And that delay is very different between the internet and real-time radio. When you're going through a repeater, always try to pause for just a second after keying your microphone. Repeaters have switches inside them, and those switches need at least a fraction of a second to activate. So if you start talking at the same time as you push the button, we may lose the first letter or a couple of letters. And what happens? Net control has to go back and has to ask, give me your prefix again, please. It got cut off. Well, it got cut off because the timing wasn't right. So give it that little pause. If you're on a linked system, which ours is not, but actually, I guess if you go through 220, it is effectively a kind of a linked system. But if you look at the Papa system, the Darn system, Cactus, Condor, any of these where they have multiple sites, the DCS repeater system, from the time you key up the node that you're talking to, which may be Wilson or Saddle Peak or something else, there may be up to 2 seconds for all the other radios to switch to the mode where they too are going to repeat what's coming in on that one node that you're talking to. So you may have to wait up to 2 minutes, or 2 seconds rather. When I run the Aries net, which is on the Darn system, a linked 70 centimeter system, I try to do that from up at my main station where I have separate radios for 2 meters and 70 centimeters. So I'm going in on one of the 70 centimeter nodes. I have the volume down, and I have good David Clark aviation headphones that seal out all the noise plugged into a 2 meter radio that is tuned to one of the 2 meter node of that system. So I don't hear what's going on the node I'm talking on. I only hear what's coming through the entire system. And I can tell if the system hasn't caught up with me yet, if somebody else is calling at the same time or on top of me. It makes it so much more efficient. And we'll talk a little bit about how to do that. But that's why you pause for those a little bit longer for those linked systems. A lot of switches have to flip in order to do their thing. It's a good idea always for net control, and often for anybody who's unsure of how well they can get in, to request a signal report before the net. And it's simple as saying, this is N6VI, can I get a signal report, please? But I want to find out whether I'm solid into the machine, whether there's a problem with my audio or there's a hum, or whether I'm noisy into the machine. There's a lot of noise on it. That means typically my signal is not strong enough to fully quiet the receiver of the repeater. If you can, run full duplex. What is full duplex? Full duplex, as I just described on my darn system Aries duties, was to listen to the repeater output or another node output on a second radio. Now, if you're within the strong range of the ACS repeater, you can do that simply. Let's say you have an antenna on the roof and you've got your mobile radio down at your desk. If you have a handheld next to you tuned to the output of the repeater, probably it won't react when you transmit on the big radio. Because remember the pattern on those verticals? Okay, nothing straight up, nothing straight down. The verticals up there, you've got a null down to your desk. You're not really in the pattern of that antenna, and besides, you're listening 600 kilohertz away from where you're transmitting. So often you'll be able to hear the output of our repeater at the same time as you are talking. So make sure the volume isn't too high up so that you don't get feedback and a squeal. That's a simple way to go duplex and tell what's going on the radio. You can tell if something comes up, and so you can stop your transmission and wait. You can tell if something's going on that you need to know. So it lets you hear if somebody else is calling at the same time you are. Now, if you're the strongest signal into the repeater, you'll hear that you're the strongest signal into the repeater because there won't be anything else underneath there. If somebody is weak, you're going to capture them into the repeater. And so you know that you can go ahead. We mentioned getting signal reports. How do you give a good signal report? First, don't look at the S meter or bars or whatever you have on your radio. Why? Because all that's doing is telling you how strong the repeater is into your radio. Your radio can't see the signal of the other operator. Your radio can only see the signal of the repeater. So you have to use your ears. If the operator is full quieting, that means there's no background noise at all in the signal, and it sounds sort of like we're doing right here. Or it may be there's a little bit of noise, but you're copying everything they say. That's good. They may decide to make an improvement, or they may decide, gee, if they're hearing me completely, that's okay, and I recognize I might have to wait my turn when it comes time to checking in. Or you may say, you're broken into the machine. I'm getting parts of what you're saying and not others. Syllables or words are dropping out. That means they need to fix something. They need to come up with a better way to get a signal in. Or you can say it's mostly noise, assuming you could copy them in the first place, where there's very little that's getting through, you're only hearing a few syllables. If you heard them clearly enough to know that they're asking for a signal report, it probably is going to be broken at worst. However, if you make out a piece of call sign and you recognize either the suffix or the operator's voice, but they don't even, most of it isn't getting through, just call them and say, hey, Joe, I can barely making it into the machine. Most of what you're saying is dropping out. You need to change something. And let them know before the net starts and everybody has to stand around while they make multiple futile efforts to be heard by net control. These are basically all techniques that you can use to make getting into the repeater and being heard better and make the net go more smoothly. Let's cover a couple of quick tech things here. The first one is offset and shift. You remember when we started, I talked to you about the repeater having a hard time trying to transmit at the same time, a strong signal at the same time it's trying to hear a weak one. The way that the repeaters resolve that is to listen on a different frequency. They can't listen on the same frequency, they'd blow themselves up. So, and by the way, a repeater is actually two separated radios typically, one in the transmit mode, one in the receive mode. Your radio and mine would have a hard time acting as an in-band repeater because it can't transmit and receive. You don't have all the necessary hardware to do that. The repeater will listen up or down the band. These are split transmit and receive frequencies. So when you refer to a split, they're separated by an offset amount. So split and offset kind of refer to the same thing. The standard offsets are 600 kilohertz, 0.6 megahertz on 2 meters. Could be 600 kilohertz up or 600 kilohertz down. On ACS1, for example, it's 600 kilohertz up. On 70 centimeters, the spread is 5 megahertz, quite a bit better, much easier to make that work because it's a much larger split, an absolute split, 5 megahertz versus less than 1 megahertz. And second, a higher percentage of the frequency. So, 70 centimeters, if you go 5 megahertz down, it's very easy with the hardware that's typically used to make sure that the receiver does not hear the transmitter at all. And therefore, it can be very, very sensitive. We mentioned these offsets. The standard offsets are built into your radios. Anything made for the US market will typically have the default. If you set up an offset, it will be 600 kilohertz on 2 meters, and it will be 5 megahertz on 70 centimeters. And I think it's 1.2 megahertz on 220. I forget the exact offset. A lot of radios come out of the box with a automatic repeater offset function, and that means when they programmed the radio at the factory, they said, oh, if he's got his dial set here, that's a repeater segment. And so he must mean, or she must mean, that they want to transmit up or down. So we're going to go ahead and put what we think it should be and leave it that way. I guess that's convenient if you really don't pay any attention to anything. But suppose we want to go to ACS2. What's ACS2? It's simplex on the output frequency of ACS1. Now, if you have this automatic repeater offset set, good luck trying to get your radio to talk on the same frequency you're listening. The automatic repeater offset is going to force you to transmit up or down 600 kilohertz. You don't want that. Most all of these have a menu item that will allow you to defeat or turn off that automatic repeater offset. I strongly suggest that one of the things you do when you get a new radio is to turn off, disable the automatic repeater offset. When you're programming the radio, you can decide if you want the offset, and if so, where. Southern California is a very RF dense environment. And that environment means that the band, particularly 2 meters, because it's not very big, is very densely packed. And one of the ways that our spectrum managers, TASMA, 2 Meter Area Spectrum Management Association, dealt with that is by having some repeaters in a segment listen low and transmit high, and others listen high and transmit low. So they're kind of staggered back and forth. There's no way that some guy in Japan or wherever they're building the radio is going to know that. You have to be in control of that. And that's why I say turn off the automatic repeater offset and understand what the actual offset requirement is, and know that you can turn it off if necessary if you want to, for example, transmit on the output of a repeater. You put in the proper shift and direction, up or plus, down or minus. Let's talk about tone encode. Back when I started using repeaters, and it was actually kind of in the early days, nobody had tones on their repeaters. You didn't need them. There were only half a dozen or a dozen repeaters in Los Angeles, and they were all in different pairs. If you transmitted frequency A, that meant you were trying to get into repeater A. But now, of course, we have so many people wanting repeaters, the coordinators have to try to co-channel them. Co-channeling means I'm going to take this pair of repeater inputs and output frequencies, and I'm going to give it to Doug, and I'm going to give it to this group over in Idlewild, and I'm going to give it to this group in Southern Orange County. We'll have each of them use a different access tone, so that when I'm trying to key up Idlewild, I don't inadvertently key up Southern Orange County's repeater. That's why we have the tones in the first place. The tone that you send determines which repeater, if any, on a given frequency pair will respond to your signal. If you have the wrong tone set, none of them will respond. And often that's one of the problems when people first program the radio. I can't get into the repeater. Well, it's because the tone wasn't set right. There are 40 or 50 tones starting with, I think, 80 something hertz and going up to a couple of hundred hertz. They're selected, there's some odd numbers in there. I mean, 100.0 is easy, but there are a number of odd numbers. And the reason is they were selected so that none of them would have a harmonic on any of the other tones. You wouldn't fool the repeater by, if there was a repeater with a PL tone of 200 hertz, and you were sending on a repeater of 100 hertz, well, the second harmonic of that 100 hertz generator could be keying the wrong repeater. So they have these tones selected so that none of them are harmonically related to any of the others. They really thought this through. These tones are referred to, you often hear it referred to as PL, which is actually a trademark term by Motorola for private line. As you all know, there's really nothing private about it. This is one of the points I try to make with CERT and Neighborhood Watch and other folks, and we're teaching them to use their FRS radios. These so-called privacy tones have nothing to do with privacy. What they mean is you become partially deaf. You can't hear any of the signals that may be on the band except the ones that are sending your tone. Now that may be convenient, but it generates all sorts of problems. So it's subaudible for two reasons. First, it's very low in volume. If you listen really closely, you can hear it. And it's very low in frequency. So you can tell your radio whether to send a tone or not. There's always an off option when you go into that tone menu. You can tell it whether to send the tone and which tone to send. And often that may be labeled tone frequency or code or something like that in your radio. And you dial through until you have the one that matches what you're trying to hit. The repeater will only retransmit your signal if it hears the correct tone. Now, interesting side note, what happens if you are sending the correct tone, but somebody who's closer and louder to the repeater and unaware that there's a repeater there is transmitting on the input? Remember, the strongest signal always wins. So you're going to start N6V, and then some other strong signal is going to come on, and for that maybe a fraction of a second or a second before the repeater realizes the signal it's hearing no longer has the right tone, you'll hear that other person retransmitted. But then it says, oh, I've given it a second and I've lost the tone. That's enough. I'm shutting off. And so you'll hear a snippet of somebody else's conversation and go away. That typically means somebody louder than you into the repeater is on that frequency but not using the correct tone, probably because they don't know there's a repeater input there, or they're trying to access some other repeater. They happen to be loud into the one you're using. So when you hear that, that's often what's happening. And by the way, ACS1 is co-channeled with at least two other repeaters that we know of. There's one in Upland, and occasionally you've heard our net control say, you know, we're going to hold off for just a minute because they're finishing up a net over in Upland. When the propagation conditions are right, we'll hear them and they'll hear us. There's also a co-channel repeater put up on the Darn system down in San Diego. Well, you say San Diego's pretty far away. Yeah, but when the tropo's in, that comes in very well to our members who are south of the Hollywood Hills. We did some experimenting with that in the past, and it wipes them out pretty well. The owner of that machine agreed to turn off the 2-meter node at the regular net times, and several of us have the control codes that we can go in, and I can shut that 2-meter San Diego transmitter off if I need to when it's interfering with our ACS net. Two more tech tips. Tone decode. Okay, remember when you go into that tone menu, there's off, there's encode, there's decode, and then they go into a bunch of digital squelch things. Tone decode means I want my receiver to not make any noise unless the transmitted signal has that tone. Our ACS1 repeater and our ACS3 repeater are transmitting those tones. So that in the event you're being bothered by another station, you can enable that and you won't hear that other station anymore. Now, as long as the repeater is louder than that other station or other repeater, that means your radio will stay quiet until our ACS machine comes on. So that's decode. But remember, you don't want that in most cases, because if you go to a simplex frequency, there are a lot of thousands of other hams who are in Southern California, and at any one time, one or more of them may be using that simplex frequency. And if you have a tone decode on, you won't know it. You'll think the frequency is empty, and in fact, you're going to be interfering with somebody else who has a right to use the radio just like you do. We discourage using that unless we specify it in the comm plan, which we do on 1, 2, 3, and 4. Last tip, the reverse function. Okay, that doesn't mean you talk backwards. It means you want to swap the frequency you're listening on and the frequency you're transmitting on. So you become just like the repeater. Instead of listening on 147.300 and transmitting on 147.900, you're going to listen on 147.900 and transmit on 147.300. Why would you want to do that? There are a couple of cases. The most common would be, let's say you have a good antenna up on the roof and a pretty decent signal into the repeater, and you know you can get in, and it's net night. And one of your fellow battalion members has a handheld, low power, and they have a lot of trouble getting in. When they're calling for any other members in your battalion, you can just hit that reverse button and listen to see if there's anybody transmitting on the repeater input. The repeater may not hear them, but you may hear them. So that's a way you can help somebody else out by listening. Let's say you guys are out in a marginal area and you're mobiling along, and one of you, you're basically getting to the point where the repeater isn't reliable, but the other person still has the repeater on. You could quickly reverse so that you're now pretending to be the repeater. You're transmitting where they're listening and saying, hey, we're losing the repeater. Let's go simplex over here, okay? So that's another quick and easy use of the reverse. Just remember to undo it when you're finished. So with that, I think we have completed most of the technical content. So why don't we go ahead and see what sorts of questions there may be out there.